Now, so I have something new to cover today. I'm going to try to do that in an efficient manner so that we have some time at the end for questions on problem set 2. Last time I handed out problem sets up to 5. If you weren't here for that, you can get them on the site. I encourage you to do that so you can see what kind of problems might be on the test. Okay. So the first definition to get out of the way, the first order ODE, our usual form, y prime is f of ty is said to be autonomous if your time derivative function f does not depend on t at all. It can only be a function of y. So what we have is y prime is some function little f of only y. Okay. Now, if you think in terms of the kinds of equations, like how we classify them, for a purpose of solving them, what kind of equation would this be? As an example, y prime is equal to y squared. That's an autonomous equation. So how would you classify that for the purpose of solving it?
Possibly separable.
It is separable. Any equation of this form is separable. And the solution, at least in implicit form, because what you do is you divide both sides by f of y. So then you have 1 over f of y dy is equal to dt. So you divide by f of y, you multiply both sides by dt, because then you can integrate both sides. So the solution is the integral from assuming you're given an initial condition, of a form y of t naught is equal to y naught, then you can plug that initial condition. You can do this as a definite integral with respect to y here, with respect to t here, and that's way to represent your solution. So assuming you're able to integrate f, or 1 over f really, and then plug in the limits, you can try to get an explicit formula, but it depends on how complicated a function 1 over f is. You might not be able to rearrange that to solve for y. Okay, so solving it is doable, but the point of this section is to see what can we learn about the behavior of a solution even if we don't have an explicit solution formula. So we're actually not going to be too preoccupied with trying to solve these, but understanding how solutions behave, especially as the initial value y naught changes. So if we fix our initial time, say t equals 0, t naught equals 0, and let the initial value y naught vary, how does that affect the behavior of a solution? And I'm going to use some examples to introduce the rest of the terminology that you'll need for this kind of analysis. You'll see how to work these kind of problems. So for our first example, this equation that we've seen before, dy dt is equal to ry. We have some initial condition, y of 0 is y naught. And we're assuming that r is positive. So this So this solution is going to exhibit exponential growth, whereas if r was negative, we would get exponential decay. So we could use an equation like this to, in a very simplistic way, model something like population growth, where r would indicate the birth rate, or the net population growth rate, so taking both birth and death into account. Now, we know, or at this point of the semester, you should know, because I brought it up before, more than once, what the solution is. Who can tell me? Yeah, well, e to the integral of r, but what's the integral of r? It's a constant. You guys can integrate a constant. RT. And RT times what? Because if I plug in t equals 0, I need to get that. Yeah. Yeah, so that is the explicit solution. Okay. Now, but if we go back to the equation itself, we will look at how dy dt behaves depending on where the solution is starting out at y naught. So if y prime is equal to 0, that is called an equilibrium solution. Because when a function has a derivative that is always 0, then if y prime is 0, then what is y? What? No, I'm not talking about y prime derivative being 0 at a single point. I mean 0 all the time. Yes, it's a constant function. So y of t is always y naught, whatever you chose for y naught. So those solutions are of interest because so that's where we have a stationary solution. That's why we call it equilibrium, that y is remaining at that value forever. Okay. So for this example, your f of y is equal to r times y. What you do is you're finding the roots of your function. So in this case, we got equilibrium solutions where? What do we have? For y equals what? So you just see where this function is equal to 0. Yeah, that's the only one. So this is a very simple example. We'll get to a more interesting one after this. Okay. Bless you. So now what you do is, and this sort of thing you do on a test problem related to this. Here we have a y-axis. It's really the y-axis we care about, not so much the t-axis. And you indicate on the y-axis where there's an equilibrium solution. Okay. And here we only have one equilibrium solution, so it's not very interesting. But if you had more than one, however many equilibrium solutions you have divides the y-axis into regions. And so in this case, let's see, we only have 2 such regions. So here we have y naught is positive and y naught is negative. So what you do is you check, is y prime positive or negative here, positive or negative here? And then you get an idea as to how the solution is behaving away from this equilibrium solution. Now, we're assuming that, because this is the only place where y prime is 0. Everywhere else has to be always positive or always negative. It's kind of like in Cal 1. You found your critical points for your derivative, and then divided up a real number line, and you had to do a sign diagram to see whether a function was increasing or decreasing. it's like that, except now it's on the dependent variable axis instead of independent variable. All right, so now that I brought back that fond memory. So in this example, keep in mind r is assumed to be positive. So over here, is y prime going to be positive or negative? Yeah, it's going to be positive. So here we have y prime is positive. And then down here, we're going to have y prime being negative. Okay. Now, so now what happens is, because in this case, y prime is positive, when a function has a positive derivative, how's the function itself behaving? What do we call that?
Increasing.
It is increasing. So if I pick an initial value over here, anywhere in here, we're going to have a positive slope, like if you were drawing a direction field. Over here, y prime is negative, so a function is decreasing. So we're going to have a negative slope. Okay. Now, in both cases, the question to ask is, how's the solution trending as t increases? It increases as it's trending away from equilibrium. Okay. And when that happens, we say that this equilibrium solution, y equals 0, is unstable. So if you get this kind of behavior on both sides of the equilibrium solution, that if you pick y naught on either side of this, it's going away from it, we say it's unstable. On the other hand, if it's trending toward that on both sides, we say it's stable. So, in fact, I would have gotten the opposite conclusion of stable if r was negative, because in this case, y prime would have been negative and y would have been decreasing. It'd be trending toward this equilibrium, and also the same on this side. Okay. Now, when you're checking behavior on either side of the equilibrium solution, I've covered a case where it trends away on both sides, trends toward it on both sides. If it is mixed, so for instance on one side it's trending away from equilibrium, and on the other side it's trending toward it, so it's not a uniform split decision, we say it's semi-stable. Okay. Now, this diagram here, it is in homework problems and a test problem, ask for this. So I need to tell you what this is called. This is called a phase line. So, what a problem related to autonomous equation is going to ask for? It's going to ask, first you find the equilibrium solutions, however many there are, so you're just finding the roots of f of y. Then it'll ask you, draw a phase line. So that means that you plot your equilibrium solutions, however many there are, on the y-axis, and then you check within the regions in between, how is the solution trending? Toward equilibrium or away from it? So I have in the notes, page 27, a sample phase line that I have right here. So I just plot the equilibrium solutions, and then I use arrows to indicate that for other values of y naught, solutions are trending toward or away from equilibrium. And I will draw another one with the next example, but I wanted to introduce all of the terminology. So here we have only one equilibrium solution that is unstable. Any questions so far before I do another? All right. This example will be more interesting in terms of equilibrium solutions. So I'm going to use this to hopefully cement some of these ideas. Or, okay, preferably all of them, of course. Okay. So next example will also be about population growth, but we want to try to make the model a little more sophisticated, get a more realistic estimate of population over time. So we still have this constant r, and we still have y in it, but now we throw in an extra factor, 1 minus y over capital K, and then we still have our initial condition that t equals 0. Okay, so R is the population growth rate, and K is the environmental capacity. So in other words, you think of it as like the maximum population that the environment can possibly sustain. And this whole equation is called the logistic equation, which has a number of applications. This is only one of them. Okay, now, so we need to find out, so this is your function, f of y is equal to r, y, 1 minus y over capital K. We need to find the equilibrium solutions. So in this case, there are going to be two of them. So where is this function f of y going to be 0? Yeah, y is equal to k, and where's the upper one? Yeah, 0. So we still have 0 from before, but now we have this new equilibrium at y equals k. All right, so now, so we'll do a phase line first, and then I'll give you, not exactly a direction field, but a graph I can show you how different solutions behave depending on the initial value. All right, so here's our first equilibrium at y equals 0, and then up here, we're assuming k is positive, because a maximum population preferably should be positive, y equals k. All right, so at these values of the initial data, the solution is going to remain constant for all time. Now, there are three regions. So we have y naught is negative, y naught is between 0 and k, and then y naught is greater than k. Now, even though not all of these may be interesting in terms of the application, but we'll cover all three of them so we can classify both equilibrium solutions as either stable, unstable, or semi-stable. Okay, so first, if y naught is negative, then we need to check, is this going to be positive or negative? Yeah, it's going to be negative because r is still assumed to be positive, the population growth. This part is negative, and then if y is negative, then this minus becomes a plus, so this part is positive. We have one negative factor, the whole thing is negative. So we have y prime is negative, so I'm going to draw an arrow pointing down, but here solutions are trending away from equilibrium solution y equals 0. Okay. Now, what about y naught greater than k? So if y naught is greater than k, then what's going to happen in that case? Positive, is this function positive or negative? Negative. It's it's going to be negative again, because here we have this fraction will become greater than 1, so 1 minus that's going to be negative. Everything else is going to be positive, so the whole thing is negative. So now we have, they get an arrow going down. So arrows going down for negative, arrows going up for positive. So here solutions are trending toward this equilibrium solution. Okay. Now, for the last case, we have y naught is strictly greater than 0, strictly less than k. So what's going to happen in that case for f of y, positive or negative?
Positive.
It's going to be positive because this fraction is now less than 1. So this is positive, that's positive, everything's positive. So y prime is positive, so we draw an arrow going up. So solutions with initial values anywhere in between here are going to be trending upward, increasing towards the solution y is equal to capital K. All right, so in fact, the arrows alone would be enough to judge whether each equilibrium solution is going to be stable, unstable, or semi-stable. So we classify both of these. So y equals 0. Look at the arrows. Stable, unstable, semi-stable. It is unstable because it's going away on both sides. And what about y equals k?
Stable.
That one is stable because on both sides the solution is trending towards it. Okay. We've not seen an example of semi-stable among these, but I can tell you where it tends to pop up is because that typically for these kind of problems, it's easiest to make f of y a polynomial that's already in factored form so that you can readily see where the equilibrium solutions are. If that factorization has a repeated factor, for instance, if I had like a y squared instead of a y, those are the kind of situations where you tend to have semi-stable solutions pop up, because you have a situation where the derivative is 0, but is not necessarily experiencing a sign change. So for instance, if this arrow had also been pointing down, that would have been semi-stable. So it's repeated factors with even powers that tend to produce that semi-stable effect. So you can kind of see that coming, like on a test problem. Okay. Is there any questions about this one? So these are kind of problems we need to solve for this material. So we don't have a solution formula for this equation yet. But it turns out you can still get some idea of how the solution behaves depending on how the initial value is chosen. So in terms of population growth, what this means is, and here we'll focus only on positive population, that generally the population is going to increase towards the environmental capacity. And as you get closer and closer to that, population growth is going to level off. In fact, world population is expected to level off at some point and then slowly start decreasing for a variety of reasons. If the population, for whatever reason, should be above that environmental capacity, it will snap back to it, just because there aren't enough resources to sustain that kind of population level. Okay. But as I've said, actually as you said, autonomous equations are separable. So this one can be solved. So I'm going to step through that because also you guys are working on solving separable equations anyway. Okay. So we have y prime is equal to ry 1 minus y over k. And actually what I'm going to do is I'm going to multiply and divide by k just to get rid of an annoying denominator. So I'm going to have r over k y and then k minus y. So it's equivalent. Okay. So now what you can do is separate this equation, put everything related to y on one side, everything it's not on the other, but everything is dependent on y. There's no t dependence here. So I'm just going to leave that constant, r over k, on the right side. And I'll divide both sides by y times k minus y. dy dt is equal to r over k. And keep in mind the initial condition, y is 0, is y naught. And I want to do this in a way that takes the initial condition into account. Now, I'm going to integrate both sides with respect to t. So I'm going to use t0 as the lower limit because my initial time is 0. And instead of changing everything to s throughout, I just use a different letter for my upper limit. I'll use a capital T. But we can get rid of t on the left side. You can think of it as canceling it into dt's, but so my substitution is y is equal to y of t, and dy is equal to dy dt dt. So we really have an integral of this dy. But therefore my limit should change. My lower limit is going to be y naught. My upper limit is going to be, instead of capital T, it's y of capital T. So these two integrals are equivalent. And then I have r over k dt. Now, the right side integral, no problem there. R over k is a constant. So I just have k from 0 to capital T, plug in limits, and you get r capital T over k. All right. Now, this integral on the left side, though, that's going to be a little bit more of a pain. How would you work out an integral like that? How did you handle that in Cal 2? Partial fractions. Yeah. So 1 over y k minus y is equal to some constant a over y plus some constant b over k minus y. Hopefully this rings a bell. So then if you multiply both sides by the denominator, then you're going to have just 1 on the left side, and then you're going to have a times k minus y plus b times y. And then what you could do in this case is when you have distinct linear factors, you can substitute a convenient value for y to figure out what a and b are. So what should I substitute in for y to figure out either a or b? Yeah, I can substitute y equals k. Whatever makes one of these terms 0. So in that case, this term is 0. I get 1 is equal to b times k. So b is equal to 1 over k. And what's the other one that's convenient? Yeah, 0. I think that's what I heard. So we get 1, and now this term goes away, and you get a times a times k. So a is also equal to 1 over k. All right, so now I can plug those values in, and so now we have 1 over k times over y plus 1 over k over k minus y, integral of that dy is equal to r over k t. And actually you have 1 over k in every single term, so all of those cancel out. So that's convenient. Whoops, that's y naught as a lower limit. So now we have that. And now we can go ahead and integrate. So this would be natural log of y from y naught to y of capital T. And then what about that? 1 over k minus y. What's the integral of that? Be careful. With a minus, because of the minus in front of a y. So you have minus natural log of k minus y is the same limits, or capital T. Okay, and then what you can do is you can substitute all the limits in, so you get natural log of y of capital T, which is what you're after, minus natural log of y naught, minus natural log of k minus y of t, plus natural log of k minus y naught is equal to RT. And what you can do is you can use the properties of logs. A difference of logs is the log of the division. And the sum of logs is a log of a product. So you can actually combine all of these into one natural log. So whatever's positive will be up top, whatever's negative will be down below. Is equal to RT, and then you can exponentiate both sides, and you get y of t, k minus y naught over y naught, k minus y of capital T is equal to e to the RT. Okay, actually, all right. On the notes I have sort of the opposite. This fraction is flipped and it's e to the minus RT, but it's still consistent. All right. I want to take homework questions, but if you, and this is worked out a little bit more in the notes, this is page 27 also. What you get for the solution is y of t is y naught times k over y naught plus e to the minus RT k minus y naught. So that comes from, if you were to cross multiply and then isolate all the y of capital T terms on one side and divide, this is what you get. So it's just an algebraic exercise from this point on. But you see, as t, capital T goes to infinity, this part's going to go away. You get y naught k over y naught. So you get, the solution tends to k as t goes to infinity. Whereas if capital T was 0, this would go away, and the y naughts would cancel, and the k's would cancel, and you'd be left with y naught. So you can see it satisfies the initial condition. But it's a long-term behavior. that I wanted to point out. You can see that from a solution formula, but you can also see it from the phase line, what happens to the solutions, because K is stable, so solutions are trending toward it. Okay. Questions on that? Homework questions? 20?
I have a general question. How far do you want us to go in the solution? Like, do we need to solve for y by itself, or if we get like y squared minus what?
If you are able to explicitly solve for y of t, you should. You won't always be able to. Like, for instance, if you have like y squared, you're talking about a quadratic equation. So in that case, yes, I would expect you to go to the square root. Also, if there's an initial condition, that indicates which is whether you choose positive or negative to satisfy the initial condition, because only one of them will. So that's a particularly important part of a problem. Okay, was it number 20? Okay. Okay. Oh, sorry, I need to make sure everybody can see this who's watching. Oh, and I keep forgetting about this. Sign the attendance sheet before you leave. So what happens in number 20 is solutions written at equations written at y squared is square root of 1 minus x squared dy is equal to inverse sine of x dx, so it's written as arc sine. So for separating, of course, you should move this to the other side. So you have y squared dy is equal to 1 over square root of 1 minus x squared inverse sine of x dx. And then what you need to do is integrate both sides with respect to their respective variable. The integral on the left requires no comment. But how do the functions inverse sine of x and then 1 over square root of 1 minus x squared, how do those relate to each other? Anybody? Yeah, this is the derivative. So with that in mind, when you have a function and you're integrating it where it's multiplied by its own derivative, how do you handle the integral? Substitution. So you let this be equal to your u, and then that integral becomes more straightforward. Now, go back to a last question that was asked. You can see when you integrate the left side, you're going to get y cubed. So there'll be cube root involved to express the solution explicitly. So like I said, it won't always be possible, but in this case, it is. I should mention number 17, you have y to the first power in your integral, which is going to give you a y squared when you integrate. So you're going to have a quadratic formula to solve for y of t, but there's initial conditions. So you must choose, is the positive or negative square root in your quadratic formula that will lead to satisfying the initial condition. We saw another problem like that before. Because the solutions to these problems are all unique. There should be one solution. There shouldn't be a plus or minus if you're given an initial condition. Any other homework questions? You also make it out a few minutes early. But it will be around later today. We'll throughout the whole day if you have any questions. A little hot up on date wheel, so that may make it interesting, but I'll do my best. Okay. So remember, whatever I find under my door when I come in the morning, is considered on time.